All right, let's start talking about some counting. So chapter 7 is about combinatorics and proofs using combinatorics and counting. And usually when mathematicians think about counting, they're not thinking about things like, you know, how many numbers are here, right? Or how many apples are in my basket, right? I can count them all, 1, 2, 3, and so on and so on. And so what they're really trying to think about is, how do I appropriately think about counting this in a way that takes, say, some set that I have and puts it into some type of correspondence with a string of natural numbers, right? So consecutive natural numbers. And sometimes it can be a little bit tricky. There's a kind of interesting question in the book that goes something like this, I think. So I have a set 25, 36, and then I think it goes to 10,000 or something like that. And the question is basically something along the lines of, how do I count this, right? How many numbers are here? Well, it gives you some information that really I'm looking at some function, right, f of n, which is n plus 5 squared. So if we think about this, right, these are all perfect square numbers. So if I square root them, I'm basically just finding an inverse function. It's going to give me, because what I have is that I could say that this set is S, right, and then f will take, right, f is defined as a function from the natural numbers onto the set S by this. And we've restricted the domain sufficiently so that, really this is actually a bijective function. And if I perform square root on any of these, right, I'll only get the positive square root back, right? Since notice my domain has been restricted to the natural numbers, right? So I could find some f inverse that goes from S to the natural numbers. And since f was bijective, f inverse is also bijective. So, I could find this, I could let f inverse of, I guess, S, that's just going to be the square root of whatever S is and then minus 5, right, outside of the square root. My S's and my 5's look very similar. So, notice that if I sort of do that, what I'll get is this value. Well, the square root of 25 is just 5, right, minus 5, so that gives me 0. And then I've got 1. And then notice if I take the square root of 10,000, well, the square root of 10,000, that's 100, right? 100 times 100 is 10,000. And then minus 5, that gives me 95, right? So it goes from 0 to 95, right? So this is my, right, this is a subset of the natural numbers. So I guess I really shouldn't say that f goes from the naturals to S, since it's only a subset of them, but no matter. At any rate, here I've got 0, 1, all the way up to 95, so there are 96 elements here, right? There we go. And I think that pretty much follows the sort of like, if it goes from 0 to n, then there's n plus 1 elements in the set. So there's 96 elements in my set. Right? So that's kind of a taste of how things work, but really what I'm going to do is I'm going to refer to this, this table up here. And this table is really going to help us focus our thinking. And they build this up in the chapter, but I'd like to go through a couple of things. The first thing I'll talk about is the multiplication principle. This comes up quite often when I want to count things. And what I can have is repeats, right? So that's fine to have repeated values in my counting. Right. So imagine that I wanted to, like, this happens, I think, with like fast food restaurants or something. They might say, like, there's this many possible drink combinations or something that you could have, or whatever. Or imagine that you go to, let's say you go to order some food, and you have, like, 3 choices for entree. Then you've got, like, maybe 4 choices for sides. And maybe you've got, let's say 3 desserts. And you've got, 2 drink options. Well, what we could imagine is that if you're going to eat, let's say you're going to eat everything, right? You're going to have an entree, right? You're going to have a side, you're going to have a dessert, and you're going to have a drink. Well, notice here there's 3, right? 4 choices for sides, right? Then there's 3 for dessert, and then 2 choices for drinks. So, like, if I have a drink, and then 1 side, and then a dessert, entree, a side, a drink, a dessert, so far, right? What I would have is 3 times 4 times 3 times 2, so that's 12, so 36, 72, right? So there's 72 basically, like, plates that I could get for myself that include an entree, a side, a dessert, and a drink, right? So this is like the multiplication principle. It sometimes will happen if you have a set where it's all the same number, so in that case, if everything is the same, then you just take the number in that sort of set and you raise it to the power of however many things there are, right? Like, let's say I'm flipping heads and tails on a coin. Well, how many possible outcomes are there if I flip 10 coins, right? Well, if I think about it, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? There's 2 options, the first 2 options, right? All the way to 2 options. Well, there are 10 things here. 2 times 2 times 2, 10 times is just 2 to the power of 10, right? Or, if I have a 6-sided die, how many outcomes are there if I'm rolling 3 dice? Well, it's 6 to the power 3, right? And so those types of things are things we can think about, right? This happens when we can have repeated things, and the order is important, right? So if you look up here, they actually use this. This actually is very similar to this thing right here, right? So notice in this table, this like 2-way table, it says are repeats okay, right? And does order matter? Okay. So I'm going to talk about this one right here. This is called a permutation, and I'll sort of build it up in a slightly different way than they have here. But one thing we can sort of think about is naturally coming along the lines of what happens in the multiplication principle if I can't repeat things, right? So let's say I have a set number of objects, right? Let's take this set, 1, 2, 3, 4, right? Well, how many ways can I arrange these numbers, right? And when I'm saying arrange them, I mean, in this case, 1, 2, 3, 4, and 1, 2, 4, 3, those are different sort of arrangements of the numbers, right? So let's say I'm going to make these into ordered 4 tuples. So how many ordered 4 tuples can I make out of this? Well, right, we can sort of think of it as a kind of a special way of doing the multiplication principle. Because if I think about how many things can go in the first sort of spot of my in tuple, right? So notice I've got a little bracket here. So I've got this and this and this. Well, I could put 4 things in this slot, right? It could be 1, 2, 3, or 4. Well, if I choose one of those numbers, right, then I can't use it in the next slot, right? So then how many choices do I have to make for the next slot? Well, for the next slot, I have to make 3. I can make a choice on 3 things, right? And then notice that this slot, I actually have, I can make a choice on 2 things there. And then finally, the last one is just 1, right? Because if I go 1 in the first slot, and then a 3, and then a 2, well, I have to pick 1 for that last slot, right? Something along those lines. So if I want to make ordered 4 tuples out of these numbers, notice I get 4 times 3 times 2 times 1, right? Right? So that's 4 times 3 times 2 times 1. 4 times 3, that's 12. That's 24. So that's 24. Right? And really, if I have, we'll say, in numbers, right? So if I have, if instead of 1 to 4, I'd gone 1, 2, up to n, right? Notice that the way I could do this as an ordered n tuple would be n factorial ways, right? And remember that this is just n times n minus 1 times, right, n minus 2, all the way up to that. Now we're introduced to this kind of interesting notation, which is when order matters, right? I mean, this will give us a slightly more general thing, right? We have this permutation, right? We've got P, right, in K. So this means if I were looking at this, right? So let's say I want to figure out if P, I'll use 4, and I'm going to take them 2 at a time, right? Well, one thing we know is that I can actually list the number of, let's say, 4 element sets, right? Or these 4 element n tuples. And something that's kind of interesting here is that if I make the set, right, I'm taking it 2 at a time. Let's say I've got the set, or I guess this is an n tuple. Let's go 4, 3, 2, 1, right? Because I can list out all of these, right? And notice I also have this 4, 3, 1, 2. All right. So if you notice, like in the definition of this, right, this is actually equal to 4 factorial divided by 4 minus 2 factorial. And sometimes it seems like kind of like, well, how do we know to divide by this 4 minus 2? Notice here, if I were listing out all of these numbers, right, 4 minus 2 is 2, right? And notice that there are two, like, sort of distinct things here where the ending, right, where the beginning is the same, right? Right, but the ending is different. Right? So really, I don't want to count this more than I need to. I don't want to count the 4, 3 more than I need to. Right? Now, we certainly could think about looking at all of the, like, these ordered tuples, right? Or just, ordered pairs of things from the set. But this is another kind of interesting way I could think about counting them. By listing out all of the 4 tuples that exist for the set 1, 2, 3, 4, and think about, well, how many things, right, are overlapping, right? How many things have overlapping stuff in the third and the fourth place, right? Or I mean, I guess how many things have overlapping things in the first and second place, right? And so notice I would get that. And so that's like a kind of a different way we can think about it, right? But I mean, either way we think about it, we'll still get the same thing. And this actually happens when order is important, right? Like if I were doing stuff, and here I'm going to go back to just doing ordered pairs, right? 4, 3, and 3, 4, right? These are different ordered pairs, right? If we're imagining that the order is important, right? These are actually distinct in their ordered pairs, right? Because they have a different thing in the first and the second, right? Even though they're the same numbers, they're switched around, right? Remember that if order matters, this is kind of what we're saying, right? These are distinct elements that we actually care about, right? So, I mean, the thing I always think about is, how do I distinguish when to use a permutation and when to use what's called combinations, right? Which we could talk about here in a second, right? But it's when the order is actually important, right? So let's actually look at combinations, right? In this case, right, combinations, these happen when order does not matter, right? And by that, I mean, if we go back to our 1, 2, 3, 4 set, and let's say I'm taking these 4 elements and I'm taking them 2 at a time, right? The sort of like 3, 4, right? And 4, 3 are the same, right? In this case, the order that I'm taking the 3 and the 4 actually does not matter. So we have to account for this, right? Sort of like how many things are actually going to do this. Well, it turns out that if I'm doing So, we had C, we could do 4, comma 2, or there's 4, 2, like that, right, where we have n choose k. Both are fine, it doesn't really matter. The notation is unimportant, as long as you understand the definition. So here what we would get is we'd get 4 factorial divided by 4 minus 2 factorial times 2 factorial. Right. So in this case, notice what we're going to have to do is we take the sort of permutation idea, right? So this is pretty much what our permutation was, and I have to divide whatever number I get there, right, by 2 factorial. So this is basically adding another way of counting any repeats, right? So just like you remember when we did the 4 factorial on the top, we're counting the number of, let's say, 4 arrangements of 4 objects. Then what we're doing is dividing by the number of arrangements that we want to avoid, like double counting, right? So where are the distinct arrangements that we want of like just 2, right? So I don't want to double count things where there's similarity, and then I have to divide through again by this number 2 factorial because we're doing them 2 at a time, and that sort of takes this 3 4 and 4 3 and this type of idea into account, right? The same thing is true with 1 2 and 2 1. Those are, for all intents and purposes, when we're talking about combinations, they're the same thing, right? The way I think about this is usually like if I was in a class and I wanted to break up students, like let's say I have let's say I have n students in a class, and I want to make k groups, or I want to make groups of size k, right, for those n students. Well, how many groups can I make? The idea would be that if in one scenario, when I choose people in a particular order, it's actually important the order I choose them in. Like, let's say the first person I choose is going to be doing the activity, the second person is going to be doing the writing, and maybe the third person does presentation to the class, right? So in that case, there would be a distinct group, right? So like if I have 3 different students, student 1, 2, and 3, well, if student 1 is in the first slot, well, that person is doing the activity. Student 2 is in the second slot, right? So student 2 is picked in the second space. They're going to be doing the writing, and then student 3 is going to be doing the presentation, right? So that's like a group. But if 3 was in the first spot, right, 1 was in the second spot, and 2 was in the third spot, that's a different, right, we'll say quote-unquote different group. I mean, their same members are in the group, but they have different specific roles within that group, right? Whereas if I just put people in a group, right, to work on something, and I had no particular order, like the order didn't matter that I'm choosing them in for roles in the group or something, then in that case, the order wouldn't matter, right? The group with student 1, 2, and 3 is the same no matter which order I choose student 1, 2, and 3 in, right? The last thing here is if order doesn't matter, and repeats are okay. My goodness, that was not great. We get this formula right here. Notice that this is just this is a combination formula, right? If I've got n elements, right, I'm taking them k at a time, that notice I've got n plus k minus 1, choose k. In this case, I'm always able to find the number of arrangements of when order does not matter, and we can actually do repeats of things. And so I think this is about it for combinatorics. The thing you need to think about here is, when is it appropriate to use these particular these particular things, right? We can think about an example. If I'm imagining, say, a scenario where I'm looking at cards, right? So imagine that what I want to do is I want to figure out, well, how many hands in poker have this particular thing, right? And something I could think about is, well, what if what I was going to do is, for this particular hand in poker, let's say I've got 5 cards, and what I want to do is think about how many of those, how many hands could I draw that are, let's say, 4 of a kind, right? So how would I go about thinking through this problem? Right, so let's think about it. Well, sort of in the one way I can think about it is, if I'm drawing, let's say, 5 cards, right? I'm really thinking about 4 of them are going to be the same. And really, what am I drawing from? Well, I'm drawing from actually quite a large, quite a large group. So let's try to think our way through the problem, right? I've got 1, 2, 3, 4, 5. Then this could be the same, and then this could be different, right? I could have it where, basically this is the same, this is different, right? And so I can have all of these sort of arrangements of the 5 cards, and this is sort of the ways that I can draw these 5 cards, right? But, right, this is not quite what we want to do. So let's think about this. Well, I can draw the cards in these ways, right? So I'm basically looking at 5 cards, right? And 4 of them are the same. So how many ways can I actually do that? Well, Notice that this is actually going to give us 5 choose 4 ways of accomplishing this, right? So that's 5, right? So this is the number of ways to sort of draw those, and I've got 5 factorial divided by, right, 5 minus 4 factorial times 4 factorial. So this actually just gives us 5, right? So it's going to be 5 ways I'm actually going to be able to draw, or well, 5 arrangements I can have there. And how many ways can I do this? Well, what I want is I want arrangements that give me, 4 of a kind, right? How many different ways could this deck be arranged to give me that? Well, in this case, notice that the order actually doesn't matter, that I'm drawing 4 distinct cards out. So I could have like, and the card doesn't matter either. So like, let's say I draw a jack and a jack and a jack and a jack or whatever, right? Or I could have like, something else like jack, something, jack, 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 whatever, right? So if I'm drawing these cards, what I have is really 52 cards, and how many ways can I draw just the cards that I want, right? And so, the first time I actually pull this out, right, I've got 4 cards I'm working with. And then the next way, I've got sort of 3 cards out of all of that, and then 2 cards, and then finally 1 card, right? So in this case, notice that a way we can actually think about this is from the 52 cards, right? I have, let me think this. You know what? I think I'm going to stop here.